So now we will go over those few numericals that are listed over here, and we would be taking them one by one. So let's start with the first one. It says that consider atmospheric air at 29 degrees Celsius. So this 29 degrees Celsius would be the value of T infinity. In parallel flow at 5 meters per second, so this would be U infinity over a 1 meter by 0.5 meter flat plate. So it is a flow over a flat plate. So we would be able to have the area 1 meter by 0.5 meter, and the plate is being maintained at a temperature of 75 degrees Celsius. So that would be Ts. Estimate the total heat transfer from the plate. So we have to find out Q, total heat transfer from the plate. So we have to find out Q. Of course it would be via convection. So we have written HA delta T. When the airflow is along the longer side and along the shorter side. So if the flow is taking over the length of the plate, and number two, when the flow would be taking place over the shorter side of the plate. And then he is also asking us that for case A, we have to find out the thickness of the thermal boundary layer. For case A means this case, and the heat flux at the trailing edge. So we have to find out the heat flux at x is equal to L as well. Now of course we would be using Q is equal to HA delta T, right? So in this case, if we are to find out the heat transfer using HA delta T and from the whole plate, so it would be H bar A, and we have to find out the heat transfer from the whole plate, from the plate. So we have to find out Q using the entire plate. So therefore in this expression H would not be local, rather it would be the average convection coefficient. So in order to find out average convection coefficient, we would be making use of one of those expressions of Nusselt number which we had seen earlier. And we know that it is the flow over a flat plate. So all we need to do is find out whether the flow is laminar or turbulent, and then we would be able to pick up the appropriate expression of Nusselt number. So first of all, we would be finding out the properties because while finding out whether the flow is laminar or turbulent, we need to find out Reynolds number, and in Reynolds number we have got this viscosity in the denominator. So we need to find out viscosity and some other parameters as well that we will come across later. For example, when after finding out Nusselt number, when we would be equating it to HL over K, we would also be requiring the value of the thermal conductivity. So in fact, usually we find out three properties most of the times. One is the viscosity nu, thermal conductivity K, and Prandtl number. But those properties would be found out at the film temperature, and the film temperature is the average temperature of Ts and T infinity. So the film temperature would come out to be the average of 75 and 29. So it would be 325 Kelvin. Now after finding out the value of the film temperature, we need to refer to the table of the properties of air, because it is air which is flowing. It may be water, it may be any other fluid such as ethylene glycol or any other type of fluid. So we need to be careful about the fluid as well, so that we can refer to the right table, corresponding table. Now in order to find out those properties, the viscosity, the conductivity and Prandtl number, we need to refer to this table, which is table A-4 at the end of our book. and it lists the properties of gases. So it starts with air. So over here in the first column we have got the temperature in Kelvin, and then we have got the density in kilograms per cubic meter, then Cp, mu, viscosity, K, alpha, Prandtl number. So over here the temperature that we have is, the film temperature that we have is 325 Kelvin. So we are given the properties at 300 Kelvin and we are given the properties at 350 Kelvin. So we need to perform interpolation. So you should revise and you should know how to perform interpolation. But over here, since 325 lies exactly in between 300 and 350, so therefore the weightage would be the same. So therefore it would be simple average. The properties would at 325 Kelvin would be the simple average or averages of respective values at 300 and 350 Kelvin. For example, if we want to find out conductivity, it is 26.3 and 30. So it would be the mere average of 26.3 and 30. Kindly note that conductivity is given by multiplying the value by 1000. So therefore the original value would be whatever the value is. So it is not 26.3, rather the actual value is 26.3 times 10 to the power minus 3. Similarly, nu is given as by multiplying it with a million. So actual value is not 15.89, rather it is 15.89 exponent minus 6 into 10 to the power minus 6. So we need to careful with the way the values of the properties have been provided. So in this way we would be able to get the nu as 18.4 exponent minus 6 meter square per second, K as 0.02815 watts per meter Kelvin, and Prandtl number as 0.7035. So now we need to first calculate Reynolds number, which is U infinity times L over nu. The free stream velocity is given to us as 5 meters per second. The length, right now it is 1 meter by 5 meter plate. So right now, since we are solving case A, so the flow would be taking place along the longer side. So the longer side would be having a length of 1 meters. And upon putting the value of nu, we get Reynolds number as 2.7 exponent 5, which is less than the critical value of the Reynolds number for the flow over a flat plate. So therefore the flow would be considered as laminar. And then since we need to find out heat transfer from the entire plate, so therefore we would be finding out H bar, and in order to find out H bar we would be using the expression of average Nusselt number over the entire plate, which for laminar flow is given as 0.664 Reynolds half Prandtl 1/3. By putting the values in, we will get Nusselt number as 307.8. And since Nusselt number by definition is HL over K, since it is average Nusselt number, so therefore it would be H bar times L, length of the plate is 1 meters, over K. K is 28.15 exponent minus 3. So therefore we get the average convection coefficient over the entire plate as 8.665. Kindly note that this is the average value of H bar. It would not be 8.6 over each and every point. If you recall that decreasing trend in the value of H, so you would realize that if it is the average value, so at some points, at some locations towards the start of the plate, the values of Hx would be more than 8.6, and towards the end of the plate the local value means Hx of the convective coefficient would be less than 8.6. Therefore the average would come out to be 8.6 watt per meter square Kelvin. And then putting this value in H bar A delta T, we will get Q as 199.2 watts. Now we have to find out Q by assuming that the flow is taking place over the shorter side of the plate, means by or over 0.5 meters. So we would consider that the flow is taking place in this particular direction, where this length in along x-axis, you may call it now x-axis, would be half a meter, and the length along this axis or ordinate would be 1 meter. Now again it would remain the same, means since we need to find out the total heat transfer, so in total heat transfer would be found out using h bar a delta t, and in order to use this equation we know all the parameters except h bar. So h bar would be calculated using this expression of Nusselt number, for which we must know Nusselt number in advance. So since we need to know the Nusselt number prior to using this expression, so we would be calculating Nusselt number using one of the expressions of Nusselt number. And since we know that the selection of the appropriate expression of Nusselt number depends upon various parameters, such as whether it is the flow over a flat plate or a cylinder or a sphere. So it is over a flat plate, that is already we know, but we need to determine the type of the flow, means we need to determine whether the flow is laminar or turbulent. So in order to determine that whether the flow is laminar or turbulent, we need to calculate the value of the Reynolds number. So by putting in the values, now the length would not be a meter, rather it would be half a meter. The rest of the things would remain the same. So we will get the value of the Reynolds number as 1.3 exponent 5, which is less than the critical value of the Reynolds number over flat plate. Kindly remember that this is 5 exponent 5 is the value of the Reynolds number, critical Reynolds number, when the flow is taking place over a flat plate. So therefore the flow would be considered as laminar, and since the flow is laminar over a flat plate, therefore the average Nusselt number would be calculated using 0.664 Reynolds half Prandtl 1/3, and by putting in the values we get Nusselt number as 217, and of course Nusselt number is a dimensionless quantity, and this Nusselt number can be written as HL over K, where H would be H bar because we have used Nusselt number bar. So we get H bar as 12.2 watts per meter square Kelvin, and by putting this value of H bar in this expression, we get the Q as 281 watts. Now in addition to finding that out, we were also told to find out the thickness of the thermal boundary layer, right? So NQS, heat transfer at the trailing edge. So in order to find out the thickness of the thermal boundary layer, we may use this expression which we had seen in the initial slides of this chapter. So we need to know, in order to find out delta T, the thickness of the thermal boundary layer, we need to find out the thickness of the hydrodynamic boundary layer along with Prandtl number. So Prandtl number is 0.7035, as we have already seen from the table, from the properties table. All we need to do is find out the value of delta. So delta at any x would be 5 times x over root of Reynolds number. Since we are trying to find out the thickness of the thermal boundary layer at the trailing edge, therefore we will also find out the thickness of the hydrodynamic boundary layer, the velocity boundary layer at the trailing edge as well. Therefore we will put x as 1 meters. Over Reynolds number was calculated over here as 2.7, because right now flow is taking place in this manner and it is not taking place in this manner. So we get the thermal boundary layer, the thickness of the hydrodynamic boundary layer as 9.5 exponent minus 3 meters, means 9.5 millimeters. So by putting in the value of the thickness of the hydrodynamic boundary layer and Prandtl number in here, we get the thickness of the thermal boundary layer as 0.01078 meters, means 10.78 millimeters. We also had to find out the heat flux at the trailing edge. So in order to find out the heat flux, we need to find out Hx, because now we need to find out the heat transfer at a particular location. So we would not be calculating the average convection coefficient, rather we would be calculating local convection coefficient, Hx. And Hx would be found out using the expression of Nusselt number, HL over K. But now it would not be the complete length, rather it would be the particular location x. However, since we are at the trailing edge, therefore x would be equal to L, means 1. And since we need to find out Hx using the expression of Nusselt number, so Nusselt number would also be local, and therefore we need to calculate a local expression of Nusselt number. So Nusselt number at any x would be 0.332 Reynolds half Prandtl 1/3 for laminar flow over a flat plate. So by putting in the values, we get the Nusselt number as 153.9, and if by putting the values in this expression, h times x over k or HL over k, we get the convective coefficient, local convective coefficient, as 4.337 watts per meter square Kelvin. And by putting then it in this expression of Q, we get Q as 99.751 watts, and if we divide it by area so as to find out the heat flux, it would be 199.5 watts, right? So it would become twice of 99.7. So that is the end of the solution. Now the next problem says that air, again the fluid is air, so we need to keep in mind whether it is air or water, so that we can refer to the correct table for evaluation of the properties at film temperature or at any other recommended temperature. So it is air which is flowing at 15 degrees Celsius, so this 15 degrees Celsius would be, this 15 degrees Celsius would be the value of T infinity at 1.8 meters per second. So this 1.8 would be the value of U infinity over a 0.6 meter long heating panel. So there is a panel which has a length of 0.6 meters. The panel is intended to supply 420 watts per square meter to the air. Now see, when it says that the panel is intended to supply 420 watts per meter square to the air, so over here it would be a constant heat flux case, because it is very simply stated over there that the panel is intended to supply 420 watts per meter square to the air. So the heat flux is constant, whereas in the previous problem it was an isothermal plate problem, but over here it is the constant heat flux problem. But the surface can only sustain about 110 degrees Celsius without being damaged. So that heating panel would have some components such that one or more of those components cannot bear more than 110 degrees Celsius. Is it safe? So we need to find out, or we need to make sure whether the temperature remains less than 110 degrees Celsius or not. And then we have to find out the average temperature of the plate. So first of all, we need to find out whether the design is safe or not, means we need to find out whether the temperature over the surface would remain less than 110 degrees Celsius. So let's first find out the film temperature. Again, the flow of most of the problems would remain the same. So we would be finding out the mean fluid temperature, the mean film temperature first, which is the average of Ts and T infinity. It comes out to be 335 Kelvin. So we can then find out the properties. Again, the three properties: nu, k, and Prandtl number. It is 335. So again, it would be somewhere between 300 and 350 degree Kelvin, 300 and 350 Kelvin. So we need to perform interpolation, right? So after interpolating, we will get the values as those that are mentioned over here for nu, k, and Prandtl number. So if we try to evaluate the Reynolds number as U infinity times length of the plate over viscosity, we get the value of Reynolds number as 0.5 exponent 5, which is again less than the critical value of Reynolds number for flow over a flat plate. Therefore the flow would be considered as laminar. Now, when it says that we need to be sure that the plate does not go beyond 110 degrees Celsius. Over here, since it is a constant heat flux problem, therefore Ts would vary. If you recall our previous discussion, if the temperature remains constant, Q would vary, and if Q remains constant, the temperature of the plate would vary. But over here, we need to make sure that the temperature does not go beyond 110 degrees Celsius. So we need to dig into this thing, that where would the maximum temperature lie or occur over the plate. So in fact, maximum temperature will occur at the trailing edge, means where the plate ends. And why it is so? Recall this diagram. The H, the convective heat transfer coefficient, decreases for the reason mentioned before. So over here, the expression is Q is equal to H times A times Ts minus T infinity. Now if Q is to remain constant, or Q by A is to remain constant, then what do we have on the other side of the equation? We have got H times Ts minus T infinity. Now out of H and Ts minus T infinity is also constant. Right, over here T infinity would have a constant, has a constant value, which is given to us as 15 degrees Celsius. So T infinity would remain constant. Now it is between H and Ts. Kindly note that the left hand side of the equation, which is heat flux, must remain constant. So with a decrease in the value of H, what do you expect the behavior of Ts would be? If there is a continuous decline in the value of H, Ts would increase, so that the product of H and Ts minus T infinity remains constant, Q by A, which is 420 watts per meter square in this particular problem. Therefore, as H is continuously declining, Ts would continuously be increasing. And since H has the least value at the trailing edge, kindly note, do not consider that H has got the least value over here, right? Because the flow is laminar over the entire plate. So what is happening over here is that this plate will end over here, and this portion does not exist anymore. So we are looking till this point only, where the flow is entirely laminar over the whole plate. So therefore H would have its minimum value at the trailing edge, at the point where the plate ends at. Therefore Ts would be maximum at the trailing edge. So we need to calculate the temperature of the plate at the trailing edge. If that temperature is greater than 110, so the plate will not be considered as safe. If that value of temperature is less than 110, the previous temperatures over here, over all those locations, would even be less than 110 degrees Celsius. So the plate would be considered as safe. Now again, since we need to find out the temperature at a particular location, so therefore we would be finding out Hx, H at a particular location, for which we would be using an expression of Nusselt number which would be local and not average. Now for laminar flow over the entire plate with constant heat flux condition, not isothermal heat condition, for constant heat flux condition, this was the expression of local Nusselt number. If you refer back to those slides, 0.453 Reynolds half Prandtl 1/3. So by putting in the values, we get local Nusselt number at the trailing edge as 94.8, and upon equating it to Hx times x over k, where x over here would be the trailing edge, means 0.6, because the total length is 0.6. So we are at the trailing edge. So therefore we get H at x equal to L, H at the trailing edge as 4.7 watts per meter square Kelvin, and then we will put this value of H in this expression of Q is equal to HA delta T. So therefore the heat flux is given to us as 420. So we will get the value of Ts from this expression as 106.8 degrees Celsius, which is less than the maximum value of the temperature that was mentioned over there in the problem. Therefore the plate would be considered as safe. And then they were also asking to calculate the average temperature of the plate. So if you recall, we had discussed this thing previously in the previous slides, where Q is h bar A times Ts minus T infinity averaged, and then h bar can be written as Nusselt number times Q over L, using Nusselt number is equal to HL over K. The rest of the things remain constant. Therefore Ts minus T infinity average would be Q times L over Nusselt number times K, right? And Q by A would then be written as Q double dash heat flux. Now the average Nusselt number, again as previously discussed in one of our previous slides, would be evaluated using this particular expression, 0.680 Reynolds half Prandtl 1/3, and upon putting in the values we get the average Nusselt number over the entire plate as 142.2. So therefore if we use again the same expression, so we get the value of this expression. So we would be able to get the value of Ts bar as 76 degrees Celsius. Now if you go over here, you can see that we were discussing this particular table where we were given all the expressions of Nusselt number. Right. So in the previous problem we had used Nusselt number as 0.664 Reynolds half Prandtl 1/3 when the flow is laminar over the flat plate, and then in its second part we had to use the local Nusselt number expression. So over here you can see that we would be referring to this particular table very often to make use of the expressions that are listed over here. Then so we would be able to get the value of Ts bar as 76. It means that the value of Ts in fact would be, you can see over here, see the value of, if the average temperature is 76, if the average temperature is 76, It means that the temperature at some locations would be less than 76 and at some locations it would be greater than 76. So you can see that the temperature at the trailing edge is in fact 106. Right? So the temperature would vary over the entire plate in this manner. It would increase. It would increase with a decrease in the value of the convection coefficient Hx, local convection coefficient. So therefore the temperature would be maximum at the trailing edge, which is 106, and it would be minimum at the leading edge. So the average of all those temperatures is 76.184 degrees Celsius. Now moving forward, the third problem involves the flow of engine oil. Engine oil flowing at 14 meters per second and 20 degrees Celsius. So 14 meters per second would be the value of U infinity, and 20 meters per degree Celsius would be the value of T infinity. Is used to cool a uniformly heated 50 centimeter by 30 centimeter plate, which is at a temperature of 76 degrees Celsius. So Ts is given to us as 76 degrees Celsius. What is the heat transfer in the first 35 centimeters of the plate? So we have to find out the heat transfer in first 35 centimeters of the plate. So the plate is in fact longer than 35 centimeter. It is 50 centimeter in length, but we have to find out the heat transfer in the first 35 centimeter from this point till this point, first 35 centimeter of the plate. Again, that would be considered as finding out Q from this entire length, and since the heat transfer is taking place via convection, so we would be using HA delta T, where H would be H bar, where you can see H would be H bar, because we have to find out heat transfer from the entire plate and not from one location. Since we have to find out H bar, we would be finding it out using Nusselt number is equal to HL over K. And since we need to find out H bar, so we would be using an expression for average Nusselt number over the entire plate. Over here, the entire plate does not consist of 50 centimeter, but it consists of first 35 centimeters. In order to select the correct expression of Nusselt number, we need to determine the type of the flow, whether it is laminar or turbulent. So therefore, Reynolds number will be calculated, for which we need to again evaluate the properties at the film temperature. So we would be evaluating the film temperature as the average of Ts and T infinity, which would be 48 degrees Celsius, means 321 Kelvin. So we would get these three values of nu, K and Prandtl number. Reynolds number will come out to be 3 or rather 0.30 exponent 5, which is less than the value of the critical Reynolds number. So the flow would be considered as laminar, and therefore the Nusselt number would be 0.664 Reynolds half Prandtl 1/3. So Nusselt number would be calculated as 1450.9, and upon equating it to H times L over K, where H would be H bar, because Nusselt number was averaged, we get H bar as 592.8 watts per meter square Kelvin, which upon putting in this expression of HA delta T will give us the value of Q as 3485 watts. So many watts or joules per second would be transferred from the first 35 centimeter of the plate. So that was a pretty straightforward problem. But over here you learned that we may also find out the heat transfer from a certain length of the plate and not from the entire plate.